All right, so I'm the last speaker. I'm going to talk about community enforcement. So just to start, let's see why this clicker. Now the clicker works. Okay, so a very important question in economics and social sciences is that can large groups of individuals sustain cooperation when people interact with different partners over time? Okay, and this question has motivated against theoretic literature on community enforcement. So what do we already know? So we know that in communities that consist of a large number of players, typically modeled as a continuum of players, then a necessary condition for players to sustain cooperation is that people can observe something about other people's past records, and by records, what I have in mind are signals about this player's past actions, as well as and also maybe signals about this player's past partner's actions. Okay, and what I'm trying to do with this paper is to think about what will happen then people can choose or can decide which signals to include in their records. And just to fix ideas, you can roughly think about restaurants trying to bribe consumers for erasing the negative reviews they posted on Yelp. And by doing this, the restaurants can potentially affect the set of reviews that future consumers can observe. Okay, and the takeaway message is twofold. So first of all, the maximal level of cooperation that a community can sustain is not monotone with respect to players' expected lifespans. So very long-lived players cannot cooperate, very short-lived players cannot cooperate, but players with intermediate expected lifespans can sustain some cooperation. And the second takeaway is that the complementarity of players' actions can undermine cooperation. Okay, and now let me get into the model, and I'm just going to show you an example. And if you want to know the general model, you can look at the paper. Okay, so I'm going to look at a repeated game over the doubly infinite time horizon. So there's no starting point and there's no end points. And I'll be looking at the steady state of the system. There is a continuum of players, and each of these players will discuss future payoffs for two different reasons. Okay. The first reason is that after each period, there will be a constant fraction of players that will be dead, and will be replaced by the same mass of new players. Okay, and the survival probability is denoted by this this parameter delta upper bar, and this is strictly less than 1. So in every period, there's a fraction of 1 minus delta bar of players who will die. Okay, and second, even conditional, I knew that I would survive until tomorrow. I still prefer to consume 1 unit of utility today to consuming 1 unit of utility tomorrow. And this time preference is captured by this parameter delta hat, and it is also strictly lower than 1. Okay. And if you are in an econ PhD program and you have taken a class on repeated games, maybe your professor will tell you that what really matters in a repeated game is this thing called a player's effective discount factor, which is defined as the product between this player's survival probability, delta bar, and this player's time preference, delta hat. This is what matters for the improved outcomes in a repeated game. But hopefully in the next 10 minutes or so, I can convince you that what matters in my model is not only the effective discount factor, namely the product of the delta bar and delta hat, but what also matters is the distinction between these two. This delta bar and delta hat will be playing very different roles in my model, precisely because players' records are endogenous. Okay, and another reason is that players' expected lifespan, namely how long they are expected to stay in the game, will depend only on their survival probability, but not on their time preference. Okay. And what's going on in each period? So in every period, all the players who are still alive, they will be randomly matched into pairs, uniformly at random. Okay, so the continuum guys and who will be alive, and these active players, they are matched to pairs. Okay, and each pair of players will play the prisoner's dilemma, And remember the prisoner's dilemma, so players can choose between whether to cooperate or defect, and cooperation is always costly, and the cost of cooperation can potentially depend on what your opponent does. Okay? And then after I take some action, you take some action, and then our actions will generate some signal that is drawn from some finite sets. And the only modeling innovation is that after I observe which signal I generate, I have the option to choose between erasing my signal or to disclose my signal. Okay? If I erase my signal, then the signal just disappears. It's not in my record anymore. And if I disclose it, it stays on my record forever. Okay? And then a fraction, what about the bar of the players will die and they're replaced by new players. Okay? Good. And an important notion is what we call record. So each player's record will consist of all the signals he generated and disclosed. Remember that every time I generate a signal, I can choose to erase it, get rid of it. Okay? And if I get rid of it, it's gone. If I disclose, then it goes into my record. Okay? And by definition, the new player's record is just the empty sets, and they have no signal in their records. Okay? And this categorical R is a set of records that a player can possibly have. And so the key stage is what can each player observe? So basically, in my model, every player gets to observe the current record of his partner. So say, for example, I match with Andrew, and then I can see his record, he can see my record. Okay? But we cannot directly observe our partner's age in the game. I cannot observe directly whether Andrew has played the game only 10 times, or 100 times, or 1,000 times. I cannot directly observe that. I cannot directly observe my opponent's identity, so I don't know who I'm being matched with. And moreover, I also cannot directly observe the timing of other players' signals. So I don't know exactly when each of Andrew's signals were generated. Okay? And of course, I cannot directly observe that, but I can infer what these things are based on my observations using Bayes' rule. So after I observe his record, I can infer what is his age in the game, who am I facing, as well as at what times he generates those signals. Okay? And player strategies has two components. The first component is a mapping from my record, my partner's record, to a distribution of my actions, either proper defects. And the second component is a mapping from my record and the signal I generate to the probability I erase that signal. Okay? And the solution concept is steady-state equilibrium, which is just a Nash equilibrium in a steady-state setting. So basically, it has a strategy, it has a distribution of records such that the strategy is optimal given the distribution of records. And if players play according to strategy sigma, then mu is a steady-state record distribution. Okay, that's the model. And now let's start from the results. Okay, and the first results is an anti-fault theorem. It shows that sufficiently long-lived players will never cooperate. So what is the statement? So the order of quantifiers is very important. So basically for every delta hat, this is a time preference. So fix my time preference to be anything that is between 0 and 1, can be very close to 1, and you give me any small epsilon, then I can find a cutoff survival probability such that if my survival probability exceeds this cutoff delta star, then the average probability that players will defect is at least 1 minus epsilon in every equilibrium. In other words, sufficiently long-lived players will almost never cooperate. Okay? So remember the order of quantifiers. You first fix the time preference, and then you set the survival probability to be very close to 1. Okay? So how come? Why is this true? Here is an intuitive explanation, and you can back out the proof from this explanation. So remember that every player has the option to erase whatever signal he generates. Okay? And given that I have the option to do so, then I can sustain my current record by just erasing whatever signal I generate. And by doing so, my continuation value must be not increasing over time. Because whenever I generate a signal that can decrease my continuation value, I always have the option to get rid of it. Okay, my continuation value is not decreasing over time. And then remember that in the prisoner's dilemma, effects is a strictly dominant strategy. So cooperation is always costly. And therefore, a player will have an incentive to cooperate only if my expected continuation value will increase by at least something proportional to 1 minus delta, right? Because my continuation value cannot be decreasing, so the only way for you to motivate me to cooperate is by increasing my continuation value by promising me a higher continuation value. How much higher? It has to be something proportional to 1 minus my effective discount factor. Okay? And therefore, if you just fix any equilibrium and we use this V upper bar to denote a player's highest continuation value within this equilibrium. And the previous statement implies that if my continuation value is very, very close to this V upper bar, then I will have a strictly standard effect. Okay? And it also implies that in expectation, my continuation value will reach the upper bar after I cooperate for a certain number of periods, and this number has to be bounded from above by something that is proportional to the inverse of 1 minus delta. Delta is the effective discount factor. Okay? And now, when players are sufficiently long-lived, namely the discount, there's about a probability is very close to 1, then one of the two things must happen. Either the players will cooperate with very low probability when they are young, or if I cooperate with a very high probability that I'm young, then there will be a large mass of players who will reach their highest continuation value because they are very long-lived. And no matter which case happens, no matter whether I don't cooperate when I'm young, or I just cooperate too much when I'm young, but there are too many old people, the average probability of cooperation has to be low because old people never cooperate. Okay? Good. Go ahead.
What happens when you do the other way around? You fix.
Okay, yes, good. If you reverse the order of limits, namely you fix a small probability set delta hat to 1, then you can sustain some cooperation. The amount of cooperation you can get in steady state equilibrium is bounded away from 0. Yeah. So basically the whole point of this is that what really matters is not just whether delta, the effective discount factor, goes to 1, but what also matters is the rates with which delta hat delta bar goes to 1. Good. So good. So 0, 1 implies that if we are sufficiently long-lived, we cannot cooperate. And if we are sufficiently short-lived, say we only live for 1 period, then obviously we also cannot cooperate because our effective discount factor is just too low. Okay. And the natural question is, will players sustain some cooperation when their expected lifespans are intermediate? Okay, if it's too long, no. Too short, no. Let's see what's going on. Then there are lifespans are intermediate. Okay, and we'll focus on the prisoner's dilemma, and we look at 2 cases separately. Okay, so remember this is a prisoner's dilemma, and the cost of cooperation can potentially depend on what your opponent does. And we say that our payoffs are weakly supermodular if my cost of cooperation is weakly lower than my opponent cooperates. So if Andrew cooperates, I find it cheaper to cooperate with him. Okay? And conversely, we say that the payoffs are strictly submodular if it is more costly for me to cooperate than my opponent cooperates. Okay? So if he cooperates, then I'm very tempted to defect. Okay? So, and in this part, I will be showing some positive results in the form that under certain conditions, then there exists some equilibrium in which we can sustain some cooperation. And for this purpose, I want to do some refinements because natural equilibrium or steady state equilibrium is too weak of a solution concept. Many crazy things can happen. And in the paper, I will focus on equilibria that are purifiable. So for those that don't know about this, so purifiable equilibrium is a refinement that helps people to conceptualize mixed strategy equilibria. Because the usual way we should think about mixed strategy equilibria is rather dumb, like I mix with a certain probability just to make Edwardian different. Why would I care about whether he's indifferent or not? Okay? And Hassani just came in and say, hey, suppose that most players have some prior information about their payoffs, and then suppose the prior information is smoothly distributed, then we behave as if we play a mixed strategy, and if it's robust, this kind of small amount of payoff information, then we say that the equilibrium is purified. Okay, and the idea is that we want to focus on equilibria that are robust. The players have a small amount of private payoff information. Okay, I will skip the definition for the interest of time, and now I'm ready to state the results. Okay, so I'm going to first introduce some bad news, which shows that if we look at purifiable equilibria that are robust to a small amount of payoff shock, then we cannot sustain any cooperation that our payoffs are weakly supermodular. Okay, it says that if our payoffs in the Prison's dilemma are weakly supermodular, I find it less costly to cooperate. When you cooperate, then all the players will always play defect in every period in all the purifiable equilibria. Okay, so you have zero cooperation. Why? The intuition is very simple. So remember from the proof of the first theorem that players with the highest continuation value will have a strict incentive to defect. Okay? And now let's just pick two players from this population. Let's say Edward, who is supposed to receive the highest continuation value, and me, I'm supposed to receive the lowest continuation value. And let's just compare Edward with me. Okay, so Edward is going to defect for sure. I may cooperate, I may defect. Okay, and now let's just pick a random person from this population that is not me and not Edward. Let's pick Andrew. Okay, so let's think about Andrew's incentive to cooperate with Edward versus me. Okay, when he meets with Edward, Edward is going to defect for sure because Edward is supposed to receive his highest continuation value already. And then, given that payoffs are weakly supermodular, Andrew will have less incentive to cooperate with Edward than his incentive to cooperate with me. Okay, and if we require the equilibrium to be purifiable, then the probability that he cooperates with me has to be weakly higher than the probability he cooperates with Edward. And then how come that Edward receives a higher continuation value than I do? And if his continuation value is the same as mine, remember he has the highest continuation value, I have the lowest, then players in this population will have the same continuation value, everyone. And therefore, there's no intertemporal incentive. And hence, there's no cooperation at all. It has to be, the level of cooperation has to be exactly zero. Okay? And in the last 2 minutes, I can show the only positive results of the paper, which says that if players' payoffs are strictly submodular, in the sense that it is less costly, it is more costly for me to cooperate than you cooperate. Okay? And suppose that each player's signal can perfectly reveal his action. Then, as long as the time preference is not too low, then we can always find a non-empty interval of survival probabilities such that if player's survival probability belongs to this closed interval, then we can find a purifiable equilibrium in which the average probability of cooperation is strictly positive. Okay? And the important thing is that this non-empty interval of survival probabilities has to be bounded away from 0 and 1. It cannot get very close to 1. It cannot get very close to 0. Okay? Why? So here's the proof. So it's a very intuitive constructed proof. So let's just divide the players into two groups. Okay? Either if you haven't cooperated before, then I call you a junior. If you have cooperated at least once before, then I call you a senior. Okay? And the strategy is such that seniors will defect against everyone, and juniors will cooperate with seniors, and when a junior is matched with a junior, then they will mix between cooperation and defect with interior probabilities. Okay? And why does this thing make sense? Why is it equilibrium? So basically, every junior faces a trade-off between having a higher station payoff if he defects versus having a lower station payoff but receiving a higher continuation value in the future. then he cooperates. Okay, and basically whenever he's matched with a senior, because he knew the senior will defect for sure, and then he will have a strong incentive to cooperate with the senior. Whereas if he is matched with a junior, because juniors cooperate with him, is higher probability, then he's just indifferent between cooperation and defect. Okay, and this equilibrium is purifiable because incentives are strict, except in a junior is matched with a junior. This is obviously purifiable, and this equilibrium will collapse. Then the survival probability is very close to 1. Why? Because if the survival probability is very close to 1, then there will be too many seniors in the population. And if there are too many seniors in the population, you don't want to become a senior because there's no benefit from becoming a senior anymore. Okay? So I'm done. It's 3:13. And thanks for coming to this session. And remember that one of the speakers cannot show up. So this is the end of the session. If there are any questions, I'll take questions.